Okay, so I'm going to put the source in this clamp here, and then I'm going to bring it up to the Geiger tube. Make sure it's absolutely right on it. Okay, just twist that so we've got the level right. Okay, so now I've got this plutonium alpha source pointing directly at the Geiger tube, and I'm going to start the Geiger counter, and you should see it's zooming away. Okay, now what we could do is we could now actually time it and see what the count is after, say, 30 seconds. So if somebody could get a phone out with a stopwatch on, we'll actually do that, and then we'll see what happens, or see what we could do with our alpha radiation to try and change that. Okay, so if I stop that, reset it. Okay, so and be ready to time 30 seconds. Yeah. Right, so ready to time 30 seconds for us. Okay, so tell me when to start.
Whenever you're ready.
Okay, so I'm starting now. So the timing 30 seconds. So this is the alpha source. It's no distance from the edge of the Geiger tube. Okay, so you can think about that. You might have noticed that on the table I do have a ruler. Okay, and that should nearly be about 30 seconds.
Coming up to 20.
Okay, so 20, 25 seconds. Just about to stop it.
4, 3, 2, 1, stop.
So we got 3,034 counts in half a minute. Okay. Now, given that the background radiation was about 30 counts in a minute, 15 should be what it should be if there was no radioactivity there. So we have definitely, obviously, got radioactivity there. So we have a ruler. Okay. So what we can do, this ruler here, we can actually change the gap between the source and the tube detecting it. So let's move it to, say, 5 centimeters. So that is now 5 centimeters. And I'm making sure it's lined up, okay? And we can repeat the experiment by doing 30 seconds again. So we'll reset the clock, okay? And any time, ready to go? Go. Okay. Oops. All right. Yeah. Okay. We'll add an extra second or so because I think I messed it up a little bit. Okay. So we're at 5 centimeter gap. This is an alpha radiation. So alpha radiation is an ionizing radiation. Does anybody know what it is? It's a particle. How long?
And we come up to 5 now. 4, 3, 2, 1. Stops.
Right. So in 30 seconds, we've only got a count of 10 now. Okay. So which is in the realms of background radiation. So basically, I would argue that no radioactivity is actually, or none of the ionizing particles have got into the Geiger tube. So none of the particles have got in. So that gap is sufficient to stop alpha radiation. Okay? So an alpha particle basically is, does anybody know what alpha particle is? It is a particle. You've got alpha and you've got beta. Okay? They're ionizing radiations. That means they can either knock electrons off or add electrons to other atoms. What do you think it means about them?
They're not very stable.
They're stable. Okay, they are stable, but obviously when they hit something else, they're going to change.
Yeah.
Okay. But if they make things positive or negative, what might they be like?
Electrons and neutrons.
One of them is just an electron. Okay, one is a fast-moving electron. And we can guess which one it is. No. Have another guess. The beta particle or beta particle is a fast-moving electron. And what charge does an electron have?
Negative.
Negative. So that's negative. What do you reckon the charge on an alpha particle is? It's positive. And it's a helium nucleus. And it's a really big thing because it's actually a nucleus of an atom. Okay, and it's got 2 protons and 2 neutrons in it. Its mass is 4, 2 plus 2. Its atomic number or proton number is 2, meaning it's helium. Okay, it's got 2 pluses, 2 neutrons. Okay, but it's had 2 electrons stripped away from it. So if it's got no electrons, but it's got 2 protons in the centre, what actual charge do you think it might have? It's positive, but how much? It's plus 2, yeah? It's positive by 2, it's plus 2, okay? So it is quite big, okay? And therefore, why is it not getting very far? What's in between it and the detector? Air. So what's happening is that the helium nuclei are smashing into air particles close to where the source is, and then that means they're being used up there. Okay, so they're ionizing the air just there. Okay, so we found that at 5 it wasn't getting through. We can now put it, in fact we can put it even as close as that, and it should make a difference. So this is about 1/2 centimetre away. Okay, we'll do a quick look at this. Okay, so if I ready to go?
Yeah.
So okay, so you can see that although that's moving quite quickly, it has reduced considerably compared to what it was before. Okay, there's no way we're going to get up to 3,000 in 30 seconds. Okay, so how are we doing time-wise?
Just come up to 10 seconds left.
10 seconds left. So possibly about half, we'll see.
5 seconds left. 3, 2, and stop.
Right, so we got just under half the amount of radiation or radioactive ions or radioactive particles reaching it. Okay, so that's something you could look at in an investigation. You could change the distance, yeah? You could be really accurate about measuring the distance. There is a track that we have where you can actually set this up on the track, set the radioactive source up on a track and move them apart very accurately so make sure they're lined up. Okay, so now what we're going to look at is we're going to see, can we stop that by actually putting something on it. So if I just leave this running now, we can see there's radioactivity going on. It's being measured. So I'm now picking up some polythene. Okay, this polythene is that in the viewfinder? Yeah. This polythene is 0.62 millimeters thick. So we've got the count spinning away there. If I put this in between, okay, it's pretty much got rid of most of the radiation. Okay, we can use a piece of paper which is 0.086 millimeters thick, and then that should also pretty much stop it. Okay, so that's our plutonium, that's our alpha source, and we've seen it's not penetrating very far. It gets stopped by something very easily, so we're going to put that away.